Zeros of polynomial functions. Fundamental theorem of algebra. It says every polynomial function of degree greater than 0 has at least one complex zero. Remember, complex zeros can be real, imaginary, or a combination of real and imaginary. And so when you start getting into these theorems and that they have below it, linear factorization, every polynomial of positive degree can be factored into linear factors. The corollary says that a polynomial of a positive degree has exactly n zeros. So we have looked at the most zeros they can have, but we're talking about real zeros. So let's say you have a quadratic that has a degree of 5. We've asked the question, what are the most number of real zeros you can have? This theorem says it actually has exactly 5. Now, not exactly 5 real, but it can have exactly 5 real or imaginary. And it will have every single time exactly the number equal to the degree, okay? And so we're moving past like just real zeros into complex imaginary zeros, right? And that's what the fundamental theorem of algebra helps you understand. This is an existence theorem, all right? Existence theorem, meaning it exists. All right, existence theorem guarantees that the zeros and factors do exist. This theorem does not explain how to find them. So we're going to talk about ways to find them. This is just an existence theorem. It literally just says the zeros exist. That's what this theorem says. All right. And then we're going to look at, well, how do you show that they exist? And more importantly, how do you find what they are? All right. So let's look at the first one, rational zero theorem. They have all this crazy stuff up here, right? This is just describing the polynomial. So this is just saying this is x to the first power, x to the next power, x to the next power down to your constant. So all these ace of naught, ace of 1, it's literally just listing out a generic polynomial, okay? Integral coefficients. So we have coefficients that are at the beginning, your leading coefficient, and you have your constant, which is at the end when it's in standard form. This is saying that C over D is going to be a possibility, I guess I should say it that way, for the zero of this particular function. So what they're telling you is if you have real zeros, or rational zeros rather, which are real, they will always come from the factors of this constant divided by the factors of the leading coefficient. That's where all of your rational zeros will come from. They will come from here. Now, obviously, irrationals will not, because by definition, irrational cannot be put in fraction form. So this is only for your rational real, right? Your imaginary zeros aren't going to come from here. Your irrationals will not come from here. But if it has a rational zero, then it will come from this particular method. So the first thing you want to do is say, well, what are my factors of my constant back here? So this last guy, my constant, is -1, all right? What are my factors of -1? 1 and -1. You'll see it written in your book like this because you don't want to write that number over and over. So positive and -1. That just means positive 1 can get you to -1, and -1 can get you to -1. You multiply them together, actually, to get it. That's the factors. Then we're going to look at our leading coefficient. Our leading coefficient is +6. What are my factors of +6? 1 goes into +6, 2 goes into +6, 3 goes into +6, and 6 goes into +6, right? And so you have to consider the positive and negative of every one of those factors, right? Positive and -1, positive and -2, positive and -3, positive and -6. Those are my factors of my leading coefficient, all right? So then what are all my possibilities for zeros? Well, I'm going to put my first one over all of my second ones. Now, it's really nice when it's just one factor there because then you don't have as many. You also have to consider the positive and negative, or the positive and negative is just going to create a positive negative, right? Positive, positive, negative, negative, positive, negative, etc., right? So you don't have to repeat it over and over. And if it ever reduces, which you'll see some of, you don't have to repeat it again, okay? So let's say I had a 2 and I had 1/3 and 2/6. Well, those are the same factor, right? So you don't have to repeat those. So if I'm going to say, what are all my possible zeros? We're talking about possible rational zeros. Well, it's going to be this guy, positive and negative 1, over every single one of these. Positive and negative 1 over positive and negative 2. Positive and negative 1 over positive and negative 3. Now, here's what I mean. This guy right here, we could just write as positive and negative 1. This next one, we can just put the positive and negative in front because those are my only options, right? And so when you do this, you just have to consider the positive and negative, but write it as simply as you can, if that makes sense, all right? Write it as simply as you can. So this would be my answer for all possible zeros here. Now, how do we know which one of those works? Because that's a whole list that I don't want to try to go through all of those, right? 8 different options. So typically when I'm doing this, if I don't know what the 0 is, I'm going to start with my positive and negative 1. That's always going to be an option because positive and negative 1 is a factor of everything, right? If you multiply 1 by itself, it's going to be one of the factors. So if you start with, and I think they started with negative 1, right? You can do your synthetic division. So I have 6x squared, or cubed, 7x squared. I don't have an x. And then I have a constant. And so I can do my synthetic division here. And you can see that negative 1 is a factor, right? And so I know that this is a 0. So I definitely know that negative 1 is a 0 because I got a 0. I also know that x minus that guy, or x plus 1, is a factor, because I got a 0 there. On your quiz, your last question was, is this a factor? You figured it out by deciding if your remainder was a 0. And so by doing that, I now know two answers here. I know 1, negative 1 is a 0. I know x plus 1 is a factor. And I also have something that I could potentially factor or at least use quadratic formula because I have a quadratic. I started with x cubed. I now have 6x squared plus x minus 1. This is actually factorable, right? Factors of 6 that multiply together to get 6 and then add together or subtract rather to get your 1. So you can actually factor this guy, 3x minus 1, 2x plus 1. If you don't know how to factor him, you can multiply across and do your grouping, or you can use quadratic formula. Quadratic formula will work. So once I factor it, I know my other 2 factors up here, right? I know that 3x minus 1 is a factor. I know 2x plus 1 is a factor. And I also know my other zeros, right? What makes 3x minus 1 equal to 0? 1/3, right? If I set this equal to 0, add 1, divide by 3. So I know that a positive 1/3 is a 0. What makes 2x plus 1 0? We'll subtract 1, divide by 2. Negative 1/2, right? I now know that negative 1/2 is a 0. And you will notice negative 1, that was one of my options right here, right? Positive 1/3, that was one of my options. Negative 1/2, that was also one of my options. Anytime you have a rational 0, it will fall in this group. This set of numbers will include all of your possible rational zeros, always. Now, here's the thing. It said rational. So if I have an irrational 0, square root of 2, it's possible. If I have an imaginary 0, I is one of my zeros. It's not going to fall in here. The fundamental theorem of algebra, though, says you're going to have exactly 3 zeros coming from that pool. You're going to have 3 zeros that will include rational, irrational, and imaginary. In this case, this told me I should have 3 zeros. They all happen to be real, okay? They all happen to be real and rational. That won't always happen, but you will always get 3 zeros, exactly. All right? Tell me all the possible zeros, and then I want you to find one and then see if you can factor. they've given us a rather large polynomial equation and they want us to solve it. When they mean solve it, they really want all the answers for x, right? So if I were to give you just I'm sure you would absolutely love for me to give you like something like that, and I said solve, you would be like, oh, she wants me to find x. That's what they mean by solving a polynomial. They want you to tell me what x could be. The difference is there's going to be a lot of answers, more than this guy over here, right? So when we solve it, we're going to have to figure out then what's going on with my zeros. And like anything else, you want a polynomial set equal to 0 to do this process. So in this case, it's not. So I really need to move that 14 over. So I'm going to have x to the 4th plus 9x cubed plus 15x squared plus 9x plus 14. All right. My possible zeros are all going to come from 14 because my leading coefficient is 1. So my possible zeros here, possible rationals specifically, are all going to come from that 14 because it's just over 1. So positive and negative 1, positive and negative 2, positive and negative 7, positive and negative 14. Those are my options, right? And so they want me to solve this. So I'm going to start with my negative 1 and see if it works. And so I'm going to do my synthetic division. I have a 1x to the 4th, 9x cubed, 15x squared, 9x, and 14. So I'm not missing anything. Start with my negative 1 and just go down, right? Bring that down. Negative 1 up, 8 down, negative 8 up. All right. Did that work? Is that one of my zeros? It is not, right? And so they actually have me move on to negative 2. Now, here's the thing. You can just start right here, right? Or actually, you can start right here. You can just ignore this guy right here if you want to. You don't have to rewrite it. And just try it again with negative 2. All right? So I'm going to do negative 2. So I'm going to go down 1, right? I'm going to make a little more room so I can do this correctly here. I'm going to make him a little bit longer so I have a place to put this guy. All right. So try with negative 2. So 1 down, right? Negative 2 up, 7. Negative 14 up, 1. Negative 2, 7. Negative 14. There we go. That one works. Does everybody see that? So I know one of my zeros then is negative 2. I know that's an option. Here's what else I know. I know that I still have an x cubed. So if I were to try to factor this thing, is it going to work? Well, kind of. Let's look and see if I have a 4 term, what's one way I could potentially solve it with 4 terms? Potentially grouping, right? It's 4 terms right now, isn't it? So if I were to rewrite this, I could say, well, that's going to be 1x cubed plus 7x squared plus 1x plus 7. That looks nice, right? So this guy is factorable. I can factor him. So if you have 4 terms, it doesn't necessarily mean, oh, I can't factor until it's a quadratic, right? Quadratic squared, you should be able to solve every quadratic. You can solve it by factoring or by quadratic formula, no matter what your answer is. Rational, irrational, imaginary, okay? But 4 terms you can't solve with quadratic formula because it's not a quadratic, okay? But you potentially could solve by grouping. And so you always want to check to see, could I solve it by grouping? If you can't, you can keep dividing synthetically from this guy forward, right? But in this case, I'm going to solve by grouping. So I'm going to group here and group here. What can I take out of the first group? X squared comes out. I'm left with x plus 7. If nothing comes out, what do I put in front? A 1x plus 7. Then my groups are going to be this x plus 7 and this x squared plus 1. All right. So I have found one of my zeros, that is x plus 2. The factor for x or negative 2 is x plus 2, right? That's my factor. I can find another 0 right here. Set x plus 7 equal to 0. What is my 0 going to be? Negative 7. So that's another 0. And I know another factor, x plus 7. All right? What about this one? X squared plus 1. Yeah, it's going to be positive or negative I actually, right? Because we're taking the square root. Subtract 1. X squared equals negative 1. Take the square root of negative 1. When variables involved, it's positive or negative I. So I have my next 0 here. Technically 2 of them. Positive and negative I. Square root of negative 1. And my other factor here is x squared plus 1. By the way, you can check this. If you were to multiply all these factors, you should get this. Well, this guy when you multiply. All right? So if it's factorable, factor them and set them equal to 0 and solve. How many zeros do I have? 1, 2, 3, 4. Fundamental theorem of algebra said I would have 4, exactly. That's what it means. No matter what set of numbers they are in, real or imaginary, you will have exactly that number of zeros. 1, 2, 3, 4. All right? All right, so Descartes rule of signs. You can also pay attention to how your positives and negatives flip to decide the number of positive real zeros and the number of negative real zeros. Now, once again, this is not going to account for imaginary zeros, right? This is only talking about real zeros, so you still could have imaginary zeros thrown in here. And this is also total possible, all right? Does that make sense? So kind of like the terms. Total possible doesn't mean that's exactly how many you will have. It is how many are possible, the most you can have or the pairs that you can have. Specifically, number of zeros is the number of variations in the sign given the initial function. And then the top number you would have could go down by twos. Go down by twos, and then you would see all the possible. And the same thing with negative. You basically plug in a negative x, and you count the sign changes, all right? It'll make more sense when we do one. So let's look at this. We have this function here. Make it a little bigger, all right? The rule of signs says, first of all, it's in standard form, 4, 3, 2, 1, nothing, right? No 0 as my degree there on the 4. And then I'm just going to literally say, how do the signs change? If they change, I'm going to count it. So when I'm looking at possible positive real zeros, and this is possible number of positive real, I am literally going to count. 3 is positive, negative 5. So that is one sign change. All right, then it goes from negative 5 to positive 4. That is another sign change. Then it goes from positive 4 to negative 10. That is another sign change. Negative 10 to negative 4 did not change signs, so I don't count that. So the total possible real is 3, or I go down by 2, 3 or 1. I can either have 3 positive or 1 positive, all right? I cannot have 2 positive, 3 or 1. It goes down by 2s. So 3 or 1 possible positives, all right? Now what I'm going to do is I am going to take this same function and I am going to plug in a negative x to all of my x's, all right? So what happens when I do that? Well, if I plug in a negative x here and take it to the 4th power, it'll be positive, and I have positive times positive 3. This guy stays a positive, all right? If I plug in a negative x and take it to the 3rd power, it will be negative, and I have a negative times a negative. That would actually make this guy positive when I'm comparing those. Take a negative x and plug it in here and square it. It's positive times a positive. This 4 stays a positive. All right? Take a negative x and plug it in here. Negative x times negative 10 is positive 10, right? There is no x to plug in here, so I can't change it. So all I've done is I've said negative x to the 4th power. Well, that's just x to the 4th. So that doesn't change. Negative x to the 3rd power, well, that's negative x cubed times negative. So you see what I'm saying? I'm just plugging in a negative x there. That's all I'm doing to see what happens to the positive negative. All right? So these are my new positive and negatives that I'm comparing. Positive, 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 negative. And then my possible number, helps to spell possible, right? Number of negative real. I'm going to do the same thing I just did with this guy. It goes from a positive to a positive. I don't count it. Positive to a positive. It still did not change. Positive to a positive. Still did not change. Positive to a negative. My only option is I could possibly have 1. I could have 1. That's all Descartes' rule of signs says. It says you can look at how the signs change, and it's an indicator of the possible number of positive and negatives you will have. All right? The conjugate root theorem. So this says if you have a polynomial with a rational coefficient and a plus c squared to b is a 0, then the conjugate, a minus c squared to b, is also a 0. If you have a polynomial with an imaginary a plus bi is a 0, then the conjugate, a minus bi, is also a 0. Anytime you have irrational or imaginary zeros, they will pair up, okay? Why? Well, irrational, square root of 2. Square root of 2 came from taking the square of an x, which means you had to consider the positive and the negative root to get that irrational, right? What is imaginary? Square root of -1, right? So if I had the square root of a negative number, I had to consider the positive and the negative root when I found that 0. So your irrational and your imaginary will always pair up. You'll always have two, the one that was given and the conjugate, okay? Always, 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 all right? So let's look at example 7. I'm actually going to jump to that one. So it says, write in standard form polynomial function of least degree with integral coefficients that has zeros, and they list it here. They have a 0 with a multiplicity of 3. So I have x, x, and x. Those are zeros, okay? Those are factors, I should say. All right, my next 0 is 2/3. Well, that means I'm going to have a factor of x minus 2/3. Okay? So far, so good. Then I am going to have the 1 plus the square root of 2. Well, that's going to be x minus 1 plus the square root of 2. But this guy is going to have a pair. It's going to be the conjugate. If they give me this one, then I automatically know that 1 minus the square root of 2 is going to also be a 0. So I have x minus 1 minus the square root of 2. If they give me this imaginary, and I know that x minus 3 minus 2i is a factor, then I also know the conjugate, x minus 3 plus 2i is a factor. So anytime you have conjugates, pair those up first. If I were to give you one this large, right, you want to pair this guy up first. It's going to be the easiest way to do it. When you pair up conjugates and you multiply these, it's going to end up canceling out, right? It's going to be a squared minus b squared when you FOIL that out. So it is easiest to group your conjugates first. Group your conjugates here, group your conjugates here, and then you'll get a nicer one because those will cancel each other out, so to speak. And then you can multiply it with the other guys, okay? So I would group my conjugates up and FOIL those. And then this would be the last thing I do, distribute that x cubed to my final answer. Does that make sense? Now, seriously, I would never give you one with this many zeros and that many pairs of conjugates. You would have like one imaginary or one irrational to pair up, right? Because this would take quite some time. If you look at the answer, it's huge. But pair up your conjugates first to FOIL.